Hi everyone, Arpit this side. In this video, I'll walk you through the dataset. We'll perform some EDA. We'll create some models. We'll also tune the hyperparameters to check which models is performing the best. And then we're going to choose that model as the default one. And then we can progress to actually hard coding the models and then reusing them later in our project. To download this dataset, go to Kaggle and search for wine quality dataset. Download it. I have already done that. And then we are going to create a folder called notebooks within our main folder. Please don't mistake it to be the apps folder. It's somewhere here inside notebooks. And then we're going to create a new Python 3 kernel. We're going to name this as my test Ep5. Alright, we're good to start. So first of all, we'll import pandas as pd, then import numpy as lp, import matplotlib dot pyplot as plt, import Seaborn as SNS from, was it scipy? Yeah, it was scipy dot starts, import z-score. Let's wait for the imports to happen. Cool. Now we're going to set professional plotting style. So we'll say sns dot set style. We're going to write white grid. Oh, trigger ID, and then plot dot rc params figure dot fig size. That's fig size. And then close it. Ten comma 6. Yeah. So the first thing that we're going to do is loading the data set. So we'll just simply use this wineqt.datasets.ef equals to pd.read under csv and use the name wineqt.csv and df.head to just get a glimpse of what we're getting. So we have fixed acidity, volatile acidity, citric acids, residuals, sugars, chlorides, free sulfide dioxides, total sulfur dioxide density, pH, sulfates, alcohol, quality, and ID. ID is just labeling, that's it. So we need to handle the ID part too. Let's drop the ID. So it's going to be if I was the D capital? No. ID in df dot columns by df equals df dot drop id and then access equals 1. It's important that you check this if statement first, because we do not want the pipeline to fail in case it has not been already removed. But if it's there, we just want to remove it. Yeah. Next, we're going to do some sanity checks. #3 dot sanity checks. First of all, print data structure next just print data dot info. Oh wait, df dot info, that's gonna be there. Next, what else we need to add? Print, I think we should check the missing values, so I'll add it to the next line. Missing values and then print df dot is null dot sum. Let's see what it looks like. Here we have missing values for each and every column. It's important that we check all this, so because if it's not well ideal, then we would like to make it ideal. So next what we want to do is we want to print the duplicate rows itself. So again, /n duplicates let's add this. Going to write I'll just use an f string. It's rather easier this way. We're going to write duplicate rows and then these curly brackets df dot duplicated dot sum. This should work. Let's see, do we have duplicate? Yeah, we have duplicate rows 125. So we should be dropping these duplicates. df dot, well, we've got a store as well, so df dot drop duplicates. Awesome. Now let's see if the length has changed. So length df so initially it was 1143 entries. Now we have 1018, so we've dropped it. Next, what we would like to print is df dot describe. All good. So let's move on to the next step. Now it's time for some EDA. We'll start with target distribution. So the idea is to plot the distribution of wine quality based on the target variable. Yeah. So first we will show BLT figure. We'll put fig size equals to 8,5. Don't worry, I'll explain the whole code a bit. We're going to add hue to the quality itself. So x equals to sns dot count plot. I think, yeah, this was it. Then we'll write x is equals to quality, and then data equals to df, hue equals to quality, and then we should have palette. I think I spelled it wrong. It's palette equals to really this, and then legend equals to false. I mean, legend is just going to give us the all values itself. We don't really want it. And next we have percentages. So we're just going to add total equals to len df, and for b in x start batches, and then next we're going to check that if height is valid or not. I mean, we do not want nan values because we want to avoid errors. So if height is greater than 0, then percentage equals, we're going to write an f string 100 multiplied by the height, and we'll divide it by total. I think 0.1f is good enough. Don't really want a lot of it. And then we'll write percentage over here. This is good. So x equals p dot get underscore x, and then plus p dot get underscore depth width is divided by 2 as 0.05. I think, yeah, that's good enough. I mean 0.05. And then y is going to be height, and then ax dot annotate percentage x comma y ha equals center, and va equals, I think it should be bottom, and then we're going to define the plot title here, title. It's going to be, let's give a very good title because we'll use this later on. So distribution of wine quality. I'll just write target variable, and then pld dot show. Am I missing something? Oops. Yeah. So it has said get GHT. Get width is not there. What's the issue here? P dot get WID. Oh. Cool, this works. Let me explain the code first, and then we can talk about the description of it. So first of all, we are just setting up the canvas. The initializing is here, and it just sets the dimension to 8 inches wide and 5 inches tall, so it's easy to read. Then this SNS count plot, it's going to tell Seaborn to create a count plot, which is essentially a bar chart that automatically counts how many times each unique value appears in a specific column. And x is equals to quality, so the x-axis will display the different wine quality scores, and then data equals to df. As usual, the data is pulling from the pandas data frame, not df, that we've created over here. Yeah, I hope this much is clear. Now the hue is depending on the quality itself, the colors basically. And palette viridress is like the color scheme, a gradient from dark purple to bright yellow to the bars. So we need to mention hue because in this newer version, I think it just throws an error if we assign a palette without using hue. So the axis is already telling us what the colors mean. So the legend is hidden to prevent the clutter itself. So if we do not hide this, oops. This will come. We don't really want that because x-axis is already showing. So yeah. Now the loop part, I mean, this is pretty apparent, right? The total is the length of tf. So in ax.patches, the bars on the chart are called patches, these bars, and this loop goes through every single bar that was drawn on the graph one by one. To get the height, we use this basically grabs the height of the current bar, which is we just here is representing the total count of the wines that is specific with that specific quality score. And then if height equals to if height greater than 0, so basically this is again a safety check. If the bar is completely empty, it skips it so that the code doesn't crash or we do not get any math errors. Now this particular path, x is equals to this and y equals to that, it's basically used to calculate the exact y and x coordinates for where the percentage text should be placed. It finds the horizontal center of the bar and slightly shifts the vertical length as well. So it just sets the y coordinate on the very top of the bar and adding some space, it's 0.05 space. This percentage is basically the calculation of the percentage, and it formats it as a string with exactly one decimal place. Let's talk about what can we observe here. So we found that as you can see that there is a severe class imbalance. So we can see 42 40, so 80, almost 82%, 82.7% of the samples being average equal to 5 or 6, right? So this insight immediately tells that a simple accuracy as a metric cannot be chosen. So I think we need to choose stratified k-fold splitting to ensure that our model actually learns to identify the rare high quality wines. So I think going with stratified k-fold over standard cross validation, because it's going to help us with this imbalance in the data set itself. So this will prevent us from data leakage and ensure that the evaluation that we're doing of the and the metrics that we are doing for the evaluation reflects the model's true performance on rare and high quality wines as well. I think for this stratified k-fold, we'll just model. We'll use the model in sklearn itself. It's called model selection, and from that within it, there's this package called stratified k-fold. We will use that. I think the k should be 5 or 10. It splits, and the loop will automatically balance it. Yeah. Now we're going to create a correlation heat map. So correlation heat map. So again, plot dot figure, and we'll put fig size equals to 12 by 10. Then we're going to close it. CORR equals df dot CORR, and then mask equals to np dot triu, and then np dot once underscore like CORR. Oh wait, also need to mention the d type. Data type equals to bool. Yeah, that's good. And then SNS dot heat map, CORR is going to be there. Mask equals to mask, and not equals to true. CMap equals to was it coolware? Yeah, it's coolware. And then we have fmt formatting as point to f, and line with ddh is equals to 0.5. Yeah, we have that. Now plot dot title, going to use chemical feature analysis. Oh, rather correlations. npld dot show. What am I missing? Mask equals to mask, annotation equals to true, CMap. Oh, yep, we have this. So in this feature selection, that we can see that the alcohol and sulfates are the strongest predictors of high quality, while volatile acidity is the strongest predictor of low quality. So these must be prioritized. So This is also the sanity check we need to do, that a strong negative correlation between acidity and pH is also there. I mean, this makes sense scientifically because more acid equals to lower pH, confirming our data is clean and not corrupt. There's a lot of redundancy as well. So I see free sulfurs and total sulfurs are highly correlated. I might engineer a single feature like a ratio or drop one to prevent my linear model from getting confused. Now we're going to start feature versus quality box plot. So before that, we need to write features to check, and then we will list down all the features. I have it somewhere over here. Yeah. And then we're going to define the plot. So plot dot figure fig size. What? Fig size equals to, let this be 14 by 10, and for I, comma, colon, n u m e r a t e features to check. Plt dot subplot quality y equals to column data equals to df here equals to quality yo. So we have this alcohol versus quality. So what's happening here is, I'll just explain the loop. Other parts I think sufficient enough for you to understand on your own. This loop basically goes through the list of our features one by one, and then this enumerate function is handy because it just gives you both the indexes I, which will be 0, 1, 2, 3, and the actual name of the feature itself, like column alcohol. And this plot, that's a plot. This command will divide our large canvas into grids, and the first two means make two rows, the second two means make two columns, so 4 by 4. I plus 1 tells that Matplotlib exactly which space to draw the current chart in. So spaces 1, 2, 3, and 4. We add 1 because Python starts counting at 0, but Matplotlib grid position starts at 1. So 1, 2, 3, 4. Anyway, now that we have it, what do we see here? So we visualize the distributions using box plots to ensure that statistical signal was real. So for example, we confirmed that alcohol showed a distinct staircase separation between quality class. So validating it as a primary predictor, whereas citric acid showed significant overlap, indicating it would be a weaker future feature. Next, we are going to do some feature engineering. So we'll just put up the heading. We'll write feature engineering. That's right. So first we will write def engineer features. Yeah, I'd like to engineer it. Data frame. Now df dot eng df underscore eng. So we will write total acidity. So it will become df dot engineered fixed acidity plus df and we also have citric acid. Yes. Next we have df. So this was basically total acidity. Next we have acidity to density ratio. So df, I think I've written it over here. I'll just write it over here. Yeah. Next is alcohol to density ratio. Wait, what? Here we go. And then we have this. It's all based on what we observed over here, here, and here. And we are going to return. We have I'll quickly get those. Yeah. So that's what we're doing. We're just trying to re-engineer the columns so that we can use this better in our wait, oh, I forgot to create a copy of it. That's gonna work. Yeah. Now that we have our data set ready for more analysis, we will start with one comprehensive analysis. So I'll simply import math, then we'll add in the features equal to column for column in df dot columns if column is not equal to quality. We just want to ensure that we include every column other than the quality itself, and then n call equals to 1 number of rows equals math dot ceiling of length of features divided by n calls. Now if we plot dot figure, I put fig size equals 15 4 into n next for I and column column and enumerate features. I will write plot dot subplot and underscore and underscore calls I plus 1 SNS dot kde plot data equals to data frame, x is equals to column, q equals quality, palette equals what was it, where it is, and then we have I think common norm. False, fill equals true, alpha equals 0.3. Distribution by quality. We will just close it over here, and in the end we will say we are doing on show. Here we go. So we have all the plots over here. Let's see. So fixed acidity goes around here. Kind of normal for 7, I guess. Yeah, 5 and 6 lie over here. So total sulfur dioxide is skewed, sulfates are skewed, alcohol is skewed, pH is close to normal along with density. So we get a very good idea what's happening over here. Now this is allowing us to compare the distribution shape of rare classes like quality heat against common ones. It visually confirmed that alcohol and volatile acidity offered the distinct distributional separation needed for a model to learn effectively, whereas features like pH almost completely overlap. So I think we have a better idea what's going on. If we would change this, would just give us a shrunken version, that's it. Now let's talk about the z-score outliers. So we need to calculate how many standard deviations away each point is from the mean. So what we'll do is we'll create a variable z underscore score equals df features dot apply score, and then outliers equals np dot abs absolute z underscore scores is greater than 3, then sum. Now plot dot figure, by this time you guys should have memorized it. Fig size equals 12, 6, and then yeah, sns dot bar plot x is equals to outliers dot index, y equals outliers dot values. Hue is as usual, we'll just write the outliers dot index palette will be, this time will be red underscore r, and then what else, legends equals false. Now we'll give plot the title, plot dot title. It's going to be count of extreme outliers greater than 3 standard devs per feature. I think that's a good enough title, and then we'll put in labels. So plot dot y label number of wines, and plot dot x label rotation equals 45, just because I want to adjust the text to be somehow be arranged in the x-axis. Now if I do not introduce the tilt, it's going to be overlapping. Now plot dot show what's wrong here? Z underscores okay, got it. Oh, legend. My bad. It should be x ticks. Yeah. So we have a lot of residuals, sugars. They are going here and there. So because of these outliers, I cannot use min-max scaler, which switches everything based on the max value. So I must use a robust scaler or a standard scaler to prevent these few extreme wines from running the scale of everyone else. I mean, ruining the scale of everyone else. Since linear regression is sensitive to outliers, it tries to draw a line to reach them, then it's going to be a problem. So this reinforces my choice to use tree-based models later. So as they naturally handle outliers by simply splitting them into their own leaf nodes. So I calculated z-scores to identify distributional anomalies, finding that residuals, sugars, and chlorides were highly skewed. So I decided that against simple min-max scaling, which would be distorted by these outliers, instead it's justified my use of robust pre-processing techniques and now non-linear tree model that are resilient to such anomalies should be chosen. Um, Now let's look at the average chemical profile by quality. So I'll write means equals df dot group by quality, then mean, then we'd like to look at means normalized equals mean minus means dot minimum, and we'll divide this by means dot max minus mean this looks good. Then as usual, plot dot figure bracket fig size equals 15 comma 8, and then SNS dot heat map means normalized annotation equals true, cmap equals close linear rather line h equals 0.5, and then we have plot dot title average feature value by quality. And then what do we have here? Let's see the chemical profile for each qualifier. Okay, so so there is a clear linear progression in features like alcohol and volatile acidity. So it's just justifying the use of linear baseline models while also exposing the nonlinear behavior between the secondary features like pH. So which confirms the need of a tree-based ensemble methods for final solution. Let's just go with the tree based because somehow I think it'll be able to cover up all these things. Next, we're going to create an interactive scatter plot. So I think I'll have to import plotly.express as px, then df equals to df dot sort underscore values by quality. Now I'm going to ensure the quality is a string so that it shows up as a distinct category on the slider and not as a particular value. So df quality equals df quality class type string fig equals px dot scatter. Now we have a couple of things to write. Okay, df x is equals to free sulfur dioxide y equals total sulfur dioxide. We need to put a comma over here and a comma over here, and then animation frame equals quality, and then we'll have color equals alcohol. Then we have size equals sulfates pH should be capital. Let's not be scientifically wrong. Density, and then we have range x equals to 0 to df free sulfur dioxide dot max range underscore y equals something similar. So it's not free, it's total. qualities, course. Show errors notebook. Let's see. Okay. So we have this over here. Okay. So when you're analyzing this relationship between free and total sulfur dioxide, I expected a strict linear correlation since one is a subset of the other. However, this plot is just showing us that um, that there is a significant horizontal spread rather than a perfect diagonal line, right? So this variance indicates that the amount of pound sulfur varies drastically between wines. This insight is critical because it is providing that we cannot simply drop one of these features due to multicollinearity. The bound sulfur variance contains unique chemical information and about that wine's preservation state. So validating that uh, we should retain both features rather than trusting a single correlation matrix which suggests they were redundant. So next we will check at the feature importance. Rather, we'll try to extract it. So extraction. So from sklearn dot ensemble import random forest regressor. Now x is equals to df dot drop yeah, quality axis equals 1 and y equals to df yeah rf equals to random forest regressor and estimator hundred random state equals 42 and now we're going to fit it rf dot fit x y yeah Now let's get the importances. Okay, the most important part. So we'll write importances equals pd dot data frame. First of all, feature x dot columns, and then importances rf dot feature underscore importances, and then I'm gonna close this one. And then I'm going to sort by values by importance and equals false. Yep. Now let's try to plot it. I've already written the plot code. Here we have it. So this confirms that the alcohol was the primary driver of quality, consistent with my EDA findings. However, unlike the linear correlation matrix, this random forest revealed that the sulfates played a larger role in non-linear decision boundaries, prompting me to retain it despite its moderate linear correlation. Next, we are going to create some models, and we're going to fit our data in it. Then we're going to compare the kappa score to analyze which one is actually doing better. Yeah. So let's start with training the first time. So from sklearn dot model selection import stratified k fold, and then from sklearn dot linear model import logistic regression from sklearn dot ensemble import random forest classifier from sklearn dot svm import svc, and what else is left? Yeah, from sklearn dot metrics import one is accuracy score, another is f1 score, and yeah, the most important one is Cohen kappa score. We might also want to import xg boost as xgb. Then next we have import light gbm as lgb from cat boost import cat boost classifier. Yeah, and then we have normal import pandas as pd, import numpy as np, import warnings. Let's see, scaling. Yeah, cool. So the reason I imported warnings was because I wanted to, mute all the warnings. So I'm just gonna write mute warnings for cleaner output. So we're going to write warnings dot filter warning ignore. Great. So first what we're going to do is convert the quality back to integers so that we don't mislabel it. I'll write it convert quality to integers df quality equals to df quality dot as type int. Then we're going to set up the data itself. So data setup x is equals to df dot drop quality access equals to 1, and then y equals to df quality. Great. Next what we're going to do is we're going to define the classifiers. Defining the classifiers. So classifiers equals to a notebook, a dictionary, random forest, and then we're going to call it random forest classifier, and we're going to write n underscore st estimators equals 100. I think random state equals 42, whatever. Next we have is let's do XGBoost. XGBoost. So we're going to write XGB dot XGB classifiers. We're going to write use label encoder equals false, and also next we want to add eval metric equals to b. I don't want to include the space. mlow class, and again random state equals to 42. Next we're going to write code for light GPM LGB dot LGBM fire. We have random state equals to 42. Here we have verbose. I don't know, I think we should do it -1. Next we have is cat boost. Right, simply cat boost classifier verbose 0 random state equals 42. As we see is support vectors, and then this is going to be SVC, I think इसमें kernel equals RBF, then C equals 1.0 random state equals 42. Yeah, that's about it. Let's try to run this. I hope we don't run into issues. Yeah, we did run into issues. What happened here? Oh, I guess, yeah. Oh, my bad. I'll have to run all of these again. Because, these features were supposed to be made, right? So, restart kernel, start all of them again. think, oh yeah, this should be good. Next what we're going to do is we're going to define the stratified key fold. Stratified key fold, so skf equals stratified key fold which is equals to 5. I think there are too many underscores. Shuffle equals true. Random state. Wow. It's gonna work too much. It's not gonna work at all. 42. And yeah. We're going to store it in results equals an empty arrow right now, and then we're going to print that starting tournament. Now, first we're going to create the first loop. So it's going to work on the the standard classifiers. So for name, model, and classifiers dot items fold underscore kappas So XGBoost needs 0, 1, 2 labels, and others are fine with 3, 4, 5. And all because we don't really need 0, 1, 2. And we can create a temporary Y just for this model. So if XGBoost in name y underscore temp equals y minus 3. So XGBoost cannot start from 3 and all, it has to start from 0. That's why we're doing this. Else y underscore temp equals just y. Now we're going to train it. For train idx test idx in skf dot split x comma y so x underscore train comma x underscore test equals x dot iloc. I hope you do know why I used iloc here and not just lock. X dot iloc test underscore idx Then we have y_train, comma y_test equals y_temp dot iloc train_idx, comma y_temp dot iloc. It's going to be test square idx. Oh wait, I forgot. Model dot fit x_train y_train, and then we'll have threads equals model dot predict x_test. Now fold underscore kappas dot append Cohen kappa score underscore test threads, then weights equals quadratic and then we're going to oh what p dot mean fold kappas, and then we're also going to write a type we're going to write print, let's do it properly, f name finished. Alright, let's try to run this. Oh, my bad. Oh, so cat boost is running, so we have this folder cat boost. Thank God the data is not that big, so the training was able to be finished in such a short time. Otherwise, we would have required a very big GPU to run very basic trainings. Next, we have another loop. Now, in this loop, we're going to do something very crazy. Okay, we'll run regressor with the rounding. Just write it. Second loop will have regressor with rounding. So let's just print LGBM regressor. So again, regressor score kappas equals to empty array LGBM underscore reg equals to LGB dot LGBM regressor random underscore state equals 42 and verbose equals -1. Now we're going to write the loop train underscore id x and test underscore id x indexes in skf dot split x comma y. Here we go. So x underscore train comma x underscore test equals x dot iloc train underscore id x comma x dot iloc test underscore id x test index, and then we have y underscore train comma y underscore test equals y dot iloc train id x, then we have y dot iloc test underscore x. Yeah, this looks awesome. Now we're going to train the regression, which is going to predict 5.4, 6.2, something like that. So LGBM underscore reg dot fit x underscore train comma y underscore train. Okay, and then continuous. Did I spell this right? NUOUS. Continuous underscore pred equals light light light. No, it's going to be LGBM underscore reg. So that's what we defined above. Then predict, and then we'll give in x underscore test. Now we have it fitted, and then we're going to predict it, and then rounded underscore threads equals np dot round, and then conti nous spreads continuous predictions, and then by and we have as type int. From float to int we'll change it. Now regressor kappas we will dot append Cohen kappa score, and then y_test, and then we're going to write rounded threads, that's what we predicted, then weights are going to be quadratic awesome. Now like before, we're going to save the result. So results dot append right model. I'll just copy from here. To write 6 dot LGBM regressor, and regressor kappas, and type is going to become regressor. Awesome. Now I think we also need to print the final. So results df equals pd dot data frame results dot sort underscore values, and then by, of course we're going to sort by kappa score, and we're going to keep it ascending. It's false because we want the best one to be coming up first, and then print results underscore df. Okay, if there is any problem over here, it's going to throw me an error. Anyway, I'll be ready for it. Oh, fit. It's supposed to be fit. Where is it? I should have just used the in Excel, but hey, just to keep it organized, I'm gonna do it all over again. That's okay. Okay. Did I define something wrong? Yep. How about I just run this over here? Yeah, there we have it. So as you can see, this is performing way better than any of the normal classifiers that we have. Of course, we still need to check the hyperparameters. We'll have to check what all can we improve. So we're going to see that next. So now we're going to optimize the models that we had just created. And to do that, we're going to use Optina. So we'll import Optina, import light GBM LGB from sklearn dot metrics, import Cohen underscore kappa underscore score from sklearn dot model dot selection, import stratified k fold and import numpy as np. So first we're going to define the objective function. So def objective trial and parameters are going to be given like so objective is regression and then metric is RMSE verbosity is equal to -1 and then boosting type will be GBDT. That's gradient based, by the way, and random state is 42. Now the things that we want to change, right? So learning rate, it's going to be trial dot suggest underscore float learning rate as now it could be anything, so I'll say 0.05 0.2. Those are the steps and the range. Then comes n estimators. So we're going to write n underscore estimators. Trial dot suggest this one's going to be an int. So an estimators, it's going to be 100 and 2000. Next is going to be max depth. Maybe 3, 15. Next, I think that comes as sub sample trial dot suggest float can subsample 0.5 1.0 and we have next is called sample by tree. I'm just gonna copy this one. This is supposed to be a float as well, and this will be also 0.5 to 1.0. Next we have rect alpha This one will be 0.0 till 1 as well. Now that we have all our objectives written, what we're going to do is we're going to write skf equals to stratified k fold and underscore splits equals 5, shuffle equals true, x equals to df dot drop quality access equals to 1, and then y equals to df quality. Next we are going to create a loop that is going to train this for train underscore idx comma test underscore idx in skf dot split comma y. We're going to write, I'll copy it from above itself, we've done this before. All of this. Next we are going to create the model equals lgb dot lgbm r e g r e s s o r, and then parameters model dot fit x underscore train, y underscore train, and then next comes the prediction part. Preds equals model dot predict model dot test, and then we're going to round this. Spreads rounded np dot round spreads, sorry, it spreads and next is score equals to Cohen kappa score. We're going to write y test tests but test threads rounded, and then we have weight equals to quadratic, and then we close it, and going to let kappas dot append the score. Return. Now we're going to return numpy dot mean of that kappas. I will just print it. Study equals optuna dot create study direction equals to maximize objective and underscore trials equals. For now I'm just gonna keep 10 because I don't really have this GPU right now with me in this system. Next, when I'll be able to implement the GPU connection and portings, and then I'll do it. So print study dot best rams and print what am I missing? OPT. Did I not install Optuna? Huh. I think I'll have to install Optuna. So I'll just write oh. I guess I'll have to do it this way. Oh wait, it's gonna be a problem. Yep, the packages are installing. Great. Okay, so this is working. I'll pause it right now. I'll come back when it's done and then we'll talk about it. So now that we have our best parameters here, we're going to use exactly these ones to get the best kappa score. And yeah, let's continue with the next part. So Optimize basically Bayesian optimization. So it's supposed to fine tune the light GPM parameters. The optimization converges or converged on a specific configuration, so a very low learning rate of 0.14 and a combined with a shallow tree max depth 3. So this outcome is significant because it indicates that the dataset contains very high variance by forcing the model to learn slowly and steadily and preventing it from memorizing the noise itself. I achieved 1.37% performance improvement from the copper score, and effectively we'll create a more robust model that generalizes better to unseen data compared to the default deeper trees. Now all we have to do is save the models that we've already created. So import joblib and import xgboost as xgb, import light GPM as LGB from skewness dot ensemble, import random forest fire from sklearn svm, import svc from cat boost, import cat boost classifier, drop t axis equals 1, y equals df dot quality as type, and now we're going to define all the models we want to do. Just copy it from the previous one. Now apart from this, I'll just include light GPM over here as well. Awesome. Now we'll print training and saving for name model in models images. Items. Now we're going to print. It's a self string. Now, if name equals xg boost of y underscore train equals y minus 3, else we have underscore train equals y. I'm going to fit the model dot fit x comma train. We'll just save file name equals f string again model underscore name dot pkl. So now I'll be saving in pkl. There are other formats to save the file. I'm choosing pkl because it's easier to pull the data out from it. And model and print. Have this all models saved. Yep, we have this. Now that we have this model ready, we're going to do is we're going to write a proper structure for training. We're going to create the utils file and everything. But in this whole video, you will be able to understand how this complete EDA works, how you're supposed to approach the data, what kind of cleaning is supposed to be done. Like in this case, the data was very easy to use. In real world, you would observe the data is not that easy to use, and there's a lot of data pre-processing that we have to do. So please take care of that as well. And I hope you learned enough to approach any data set on your own now. Yeah, that's it for this. Thank you.